Okay, good morning, everyone. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, as expected. So it's going to be groups of 2. Any questions from the induction session before we start? No? Perfect. So let's begin with start the business, really. So, laminate theory, I think that's the principle and the skeleton of what we need to do, we need to know for composites. Although it might look and sound quite complicated, it's a lot of mathematical formulation, it is what it is, composites, so you've got to know it. If you don't know it, you know nothing about composites. Let's put it this way. So, in this session, we will delve into the mechanical behavior of composite materials, obviously static linear material, static linear analysis, and then obviously we'll go one step at a time. My intention is to finish the entire content in one session. Maybe I'm being too optimistic, I don't know. We'll see. We might end up carrying it on for the next session a bit, but we'll see anyway. Because it is quite critical for me that whilst we're going through the theory, you will go through some examples, so that you can consolidate your theory based on examples. I don't want me be the person talking all the time, you listening to me and get bored, which will happen, I'm pretty certain. But yeah, I want you to do something and learn it as we go along. So the intention is that in the sessions that we have, in the 12 sessions, that reduce or minimize the amount of self-study that you would do outside this classroom, but you can't avoid it. Okay, composites, let's begin. What are composites? What's the first thing that comes to your mind? Yeah.
A material that's made up of two separate materials, usually a matrix and I can't remember the stiff part. Not stiff part. Reinforcement. That's
reinforcement.
Yeah.
Okay. So, and why do we do that? What's wrong with using steel or aluminium? What was wrong with that? Would that be made manufacturing aircraft? Again, I'll be using a lot of aerospace examples because I'm an aerospace guy. We just apply it to other mechanical, automotive, and other sectors of industry. But what was wrong with steel and aluminium that we used to manufacture aircraft for 70, 80 years now? But what happened then? It's just the weight?
Weight, isn't it? Like relative stiffness, etc.
Relative stiffness. You're saying the right things, but not the exact technical terms that we want to hear. Anything else you think of the problem with metallic conventional materials that we have today, or we had in the last 70 years? We've been privileged to have them, and then we decided.
Like the layers of metal slipping, like falling apart, because there's no like things in the material to block the movement of the layers. Well,
differences. Well, you're saying it's got a different failure mechanism, but it's not really. In fact, metals have got superior failure mechanism compared to composites, as we will see in the subsequent lectures. That's one of the advantages of the metallic materials, in fact.
Pressure, altitude, it's like loading.
And what happens?
You load it a couple thousand times and it fatigues the metals.
Yeah, it's got enhanced fatigue performance. Yeah, it's a lot better in terms of fatigue. One of the key things that we see day in day out, basically, is corrosion resistance. So most of the aircraft we see today in service, A320, A319, A380, and I deal with them on a daily basis. The common, 90% of the problems we're having with this kind of aircraft is corrosion. It's made of aluminium, high-strength aluminium, 7000 series. Supposed to be not corrode, well, it's called corrosion resistant, but aluminium does corrode. It doesn't mean, steel does corrode, aluminium does corrode, aluminium corrodes less than steel. So when you see aircraft in service after 15, 20 years, comes with a lot of corrosion and you have to repair it. So one of the key advantages of composite is that it doesn't corrode. So if you imagine if you've got an aircraft, or particularly if you see a Navy ship, for example, in salt water, which you've got chloride, fluoride and all of that, will facilitate or catalyze corrosion. If you've got a composite, none of that's going to happen, but it's got its defects and problems that you need to deal with. Okay, so let's get on with the main part of things. So composites are essentially a material system made of 2 different or 3 different, 4 different, it doesn't mean 2 different systems. It could be 4, 5, 6, 7. And the key is that you amalgamate the strength of each component or its constituent to come up with a superior material. So, as your friends rightly suggested, it's often comprised of reinforcement. Yet again, that reinforcement could be carbon, could be glass, could be a combination of both, could be Kevlar, could be metals, in fact. And you've got a matrix that bonds everything together. So the whole concept of having a matrix is to transfer the load from reinforcement, one reinforcement to another, and also to bind everything together. Essentially, it's a binder. The matrix is a binder. So I think it's a sort of informative table. In terms, when it comes to the matrix, you could have. Hopefully this works. I haven't worked with it for a long time. Doesn't work. Pen. Okay, so you could have organic matrix. Basically, it's organic material as a matrix. It's not synthesized, as you see there. For example, cement is kind of organic matrix. It could be a mineral matrix. Examples are all in here for you. For example, concrete is a good example of that. You've got gravel, sand, gravel, and then you've got cement binding the whole thing together. Composite is essentially one of the oldest composite materials you can think of, concrete. You could have the matrix be a metallic. So it is possible to melt metals, a molten metal, which could act as a matrix. So that could be, and they are very important, particularly in high temperature environments, particularly for rockets and space programs. They use a lot of that. And also you can have sandwich structures, which you have a core. I don't need to explain it, probably you know it already. You have a core and you've got other composites as the face sheets. This is a good example, and I think quite important. I just tried to put some examples as well. For example, this is a good example of a composite material made of graphite, or we call it graphite, and silicon carbide powder. So essentially, what they end up doing in a wet ball milling, they try to make them into powder. The same with the graphite, combine them together into reinforcements. So you can see graphite surrounding the silicon carbide, and it will come up with essentially a composite. And then you will have aluminium matrix surrounding the whole structure, and this will be a kind of, they call it SiC, silicon carbide graphene core shell nanoparticles. It's a composite. So when you hear composite, it's not just carbon fiber reinforced polymers or glass fiber reinforced polymers. It is a very high strength composite, for instance, which could be used in high temperature environments. Again, engines, aircraft engines, space programs. As an example, the silicon carbide, why they use it, for instance, as you can see, the silicon carbide has got a very high strength and stiffness. The modulus of elasticity of silicon carbide is 1 terapascal. If you compare it with steel, how much is the steel? Modulus of elasticity of steel, how much is it? 200. So it's considerably higher, right? Considerable. Also, you have, if you look at the strength of silicon carbide, is 130 gigapascal. And how much is the strength of steel? Any ideas? You will take? And give a number, just for a number.
1.3 GPa.
400, 500 megapascal, maybe 600 megapascal, depending on the grade of steel. And you can see the difference is huge. So they're using silicon carbide, which is very strong. The stronger the material gets, the more brittle it becomes. So, but it becomes brittle. To compensate for that effect, they'll add something like aluminium as a matrix to make it more ductile. So they're taking the advantage of each component, mix them together, you will come with a super material essentially. That's the whole concept. So they use aluminium, it's ductile, lightweight, corrosion resistant, and has outstanding conductivity. So they could use that essentially because graphene or graphite has got a very good electrical conductivity. The same could be said of silicon carbide and aluminium. So essentially you will come up with a composite which is not only good for high temperatures, it also conducts electricity. So where you need, for example, if you've got aircraft which needs, not that it's being used, but for aircraft which needs lightning protection. So the lightning strikes, that needs to be diffused. So if you've got something which has got high electrical conductivity, that will help you achieve that. Just one example. One of the things that has recently, is becoming more of a trend, or it's been in the past, but we paid little attention to, are biocomposites. Nowadays they're trying to make use of biocomposites, for example, for the aircraft seats. Make them lighter, and it doesn't need to be unsustainable, maybe the right word. So they're trying to be sustainable by using biocomposite. An example is inorganic cement board. So essentially what you have is cement mixed with bamboo fiber. Bamboo fibers are absolutely amazing. I had a PhD student working on it, and it was essentially trying to replace steel with bamboo fibers for building construction. I'm trying to be as close as possible with the laptop as well, so that my voice can be heard, hopefully. Don't shoot me if the recording does not work, okay? I'm trying. Another example is bamboo MDF. You've heard of MDF, they use for cabinets manufacturing, or wardrobes, they use MDF. So they can use bamboo fibers, mix it with thermoplastic propylene matrices or resin. So it becomes the kind of composite that you can make use of. You can use bamboo flakes in terms of sandwich structure. So you've got a foam and you've got flake boards as the face sheets. All of these are composites, okay? But we're not going to talk about every single one of them individually. So we're going to look at the high-performing composites of carbon fiber reinforced polymers or glass fiber reinforced polymers. And once you know those, dealing with this will be a lot simpler in terms of characterizing the mechanical behavior of these things, okay? Any questions so far before I carry on? I don't want to lose you in the middle of the wall. No? Yeah, please interject me. If you've got any questions, don't be afraid of putting your hand up or just jump in, that's fine. So composites are classified based on by the formal constituents. So the constituents could be fiber composites. So the reinforcement could be fibers. These are the ones that we will be dealing with in this module, or they could be particle composites. So with respect to fiber composites, the fibers could be, as you saw in the case of bamboo, it could be short fibers, it could be long fibers, continuous they call it, or discontinuous. And that's what we will be dealing with in this lecture. The particle composites are essentially, as I explained for silicon carbide, you will have a sort of round reinforcement. You can see concrete as a kind of particle composite, or silicon carbide inclusion. Or ceramic composite, in fact. One of the good examples of this is called ceramides. Ceramides are essentially a mix of, and again, these are being used in space programs. There are a combination of ceramic material and metal. So the combined name, they call it ceramides. So the ceramic material has got very high thermal resistance. So where you've got the rocket engines. Any ideas for rocket engines? What's the temperature like? I mean, what kind of temperature we're talking about when we're talking about the nozzle of a rocket, or let's say hypersonic missiles?
3,000 degrees.
Exactly. So if you've got 3,000 degrees Celsius, you can't use steel. You can't use even titanium. You can't use any metallic material. Even if you create a sort of thermal barrier, still these temperatures are ridiculous. So you do need to resort to a kind of material that can withstand these high temperatures and high environments. And one of the key things is that with high temperatures, you've got a phenomenon called creep. And probably the creepy word comes from that. So essentially creep, probably you know, is just structure straining under a constant load, deformed The load is constant, but it keeps deforming. So at high temperature, that does happen. Okay, there is another classification for composite, is that what the matrix is organic, so organic matrix composites. The fibers could be mineral fibers such as glass, carbon, Kevlar. You could have organic fibers, polymer and Kevlar. You could have metallic fibers, boron, aluminium, etc. These kind of composites, I've seen them being used for where, so these boron, aluminium sort of things, where you've got impact. And also Kevlar, you know, with anti-bullet vests and stuff. So where you've got high impact and you need high ductility material, you use them. The matrix could be a metallic matrix, as I said before, previously mentioned. The fibers could be, again, mineral fibers, carbon, silicon carbide. We saw an example of this before. It could be a metallic fiber, boron, and it could be metallo-mineral fibers, boron fibers coated with silicon carbide. So it just, the sky is your limit. Mix and match, see what it comes up with. Essentially, that's what it is. Okay, so it's all experimental based. Just mix them, different ratios, and just essentially it's chemistry really. Just put them together, see what happens. The matrix also could be a mineral matrix composite, which, yet again, metallic fibers could be used for those. Metallic particle ceramides is one of the famous ones, and you could use nitrides and carbides as the mineral particles. So that's another classification. I'm sorry. That's my daughter calling me. I don't know why. She should be in school. There you go. Maybe she's not in school. I don't know. So, if you look at these two terms are quite important. Maybe that's where you can get the why composites are critical, are important, not critical. So, if you look at steel, aluminium alloys, wood, glass, tungsten, beryllium, in terms of modulus of plasticity, you can see tungsten and steel are, and maybe beryllium are the top ones. The ultimate strength is given 340, as I said, steel between 340 to 2,100. So something in between at the average. The density is also given. Specific modulus that I would like you to focus on, and specific strength for all these metallic materials. On the other hand, if you look at the composite ones, E-glass, S-glass, carbon, CFRP, Kevlar, boron. Okay. If I were to ask you, what is the superiority of composites with respect to the metallic based on these characteristic information? What would you say? Which one of them you think is clearly showing superiority of composite to metallic? Because there's a misconception about composites and metallic, and that was the reason I asked you the question: why are composites better than metallics? Can you see from the numbers the common denominator here, maybe, or yeah? Yeah. So when somebody asks you why composites are better than metallics, it's not because they're stronger. If you look at E-glass, 72 gigapascal. If you look at steel, 210. Clearly, steel is stronger. Okay, but its density is a lot higher. So it's the specific strength of composites that make them special. So the strength you get for the amount of material you use. That's why it becomes lighter. So that's the specific strength that we care about. If you look at the glass, we're talking about 1,380, 270. 6 times as much almost. 6 times as much as steel. If you look at carbon, high strength carbon, that's the one we use for aerospace, 1,800, let's say 2,000. It's not even comparable with what you get here. So that's the specific strength that we really value when it comes to composites. There's also something that some people do ask, is that you've got E-glass and S-glass. What are the differences, you think? What's the difference between what's E-glass, what's S-glass? If you know you've done some composites in the past in your degree, what's E-glass or S-glass? Yeah, you can use your search or your laptops. Just. I'll give you 2 minutes, and I would ask one of you to just tell me what's the difference between e-glass.
High-performance glass fiber and e-glass is electric glass. It's all just glass, isn't it? Yeah. Technically, the computer's just a big thing. No, that's silicon.
I got my information from glass blowing for beginners.
It was glass and wine blowing.
Ew, disgusting.
It's quite easy.
What's trusted? I don't know.
That's just the matrices and getting references.
You cannot trust it.
And you definitely can. Like I said,
Simon said, you don't trust it. His best friend.
no, I don't trust it. I do trust it.
Baby degree.
I just loved when we were in the
my degree
and
is
you were
very
trying to get it to make an entire presentation.
I did.
Okay, so what's up? So, what's your conclusion? I think. What's that?
Made with silica-based things, and one's made with silicon, and one has other oxides in it as well. That's as far as I got.
Okay, that's one part of it. Yeah, go on.
One's cheaper than the other.
Which one's cheaper?
E-glass.
Okay, why?
Because I'm sure you use aluminium.
Okay, so in terms of your engineers, okay, so you're dealing with strength numbers and structural applications. Which one's which? Which one's what's the application of each one? Go on.
E-glass has low electrical conductivity, and
Mhm.
S-glass has high tensile strength.
Yeah. So, as its name suggests, E-glass is electrical glass. S-glass is structural glass. So, E-glass is heavier. So the density is around 2.54 roughly gram per cubic meter becomes. And then S-glass is around 2.48. So it's lighter. Okay. As its name suggests, S-glass is a structural glass, which is stronger. So you look at the modulus, 70 to 85. So S-glass is pretty much the same as aluminium. Where's aluminium? 70, 72. Okay. Yeah, it is well, because if you look at aluminium, what's the aluminium is 52 to 230, that one is 1,000. Yeah, even compared to aluminium, that all the aircraft we've got today in service are made of, not all of them, I mean, majority, but aluminium alloys, which you can see, even if you made them of E-glass or S-glass, they would be significantly lighter. Okay? But obviously, we don't do that because of the safety issues. So, E-glass can go to up to temperatures of 300 degrees Celsius. S-glass 450 degrees Celsius, so it's considerably higher. Cost, you mentioned the cost. Applications. So based on what I said, where do you think we use E-glass and where do you think we use S-glass? What?
Applications.
Yeah, yeah.
E-glass for stovetops, and glass stovetops.
Okay. Yeah. Yeah. Okay. That's glass. So e-glass, as I said, general purpose. Bolt holes, they use it for e-glass. Pipes, structural components, but S-glass is, as I said, is structural. So we use for high-performing structures, such as aerospace components and defense armor, because it's stronger and lighter. For wind turbine blades, which one do they use? E-glass or S-glass? S-glass. So evidently. So in applications that you have, you want so e-glass has got more electrical resistance. So if you want to create electrical insulation, e-glass is best used. So if you look at the electrical masts, they use e-glass as opposed to S-glass. How do I go to the next slide? There you go. So another classification is based on the fiber. So we talked about the matrix form, now the fiber forms. The fibers are essentially, I've created sort of carbon fiber. The diameter of the fiber is around micrometers. In this case, 6 micrometers. They can't be used as the structural reinforcement as they are. So we need to bundle them together to create, as they call it, strand or yarn. So that fiber of that tiny fiber, that single isolation of fiber, we call it monofilaments. Once you put a lot of them bonded together, bundle them up, it becomes strand or yarn. So these are the terminology that you need to know as you start working with composites. So, and the carbon yarn would look like this. So essentially each of these yarns is comprised of thousands of these carbon fibers, which are quite narrow. So in terms of surface tissues, or the topography of composite that we have, these strands and yarns that you see there could be in different configurations. They could be in the configuration of mats, woven fabrics, and ribbons. And these are the ones that you mostly see in terms of manufacturing. So mats, woven fabric, and ribbons. Let's see what these are. Just maybe an illustration. I'm not possibly going to go through it, but you've got the filaments, as we said. You can either have continuous fibers or discontinuous fibers. For highly load-bearing structures, you go for this, because the load pass is continuous. Once one of the fibers is loaded, it transfers the entire load along the length of the fiber. There is no discontinuity. Whereas the discontinuous fibers, loaded, interjects here, doesn't know where to go. So it needs to go through the matrix and back to the next fiber, and that creates a weak point, discontinuity, or we call it stress concentration as well. You can have these continuous fibers as mats, we will see what they are, or you can just have it as textile filaments, which then become woven or a strand. Mats. Probably you've seen this kind of mats, glass mats. Now sheets, continuous or discontinuous, as I explained in the previous slide. In this particular case, you see discontinuous fibers distributed in a plane, and often they're impregnated with resin. Whilst under pressure and temperature, the whole thing bonds together. Okay. In terms of mats, you can have chopped strands or continuous strands. The chopped strands is very difficult to deform. One of the problems with composite is that if you've got a double curvature structure, like sphere, or the nose of an aircraft, okay, where you've got the radar, it's double curvature. If you imagine you've got a fabric, you try to mold the shape of that thing, you have a lot of creases. So you need something quite flexible to be able to form, to adapt to the shape of your structure. If you're using chopped strands, it's very difficult, it's not flexible. It doesn't allow you have a lot of creases and you can't just form it or shape it to the right shape. With respect to the continuous strands, that problem goes away. So you will have a lot more flexibility to stretch it in all directions to give the good mold. This is quite important. This is like the one after that. Is that in composite terminology, we've got these if you could call it ribbons or yarns. These yarns that run across the mat. So this is the mat. They're called wefts. You should know it from now on. So the crosswise ones are called weft. And the lengthwise, which is in the loading direction, we call it direction 1 of the material. So direction 1 and direction 2. So direction 1, length of the material, the loading direction, we call it warp, weft warp. So the way these wefts and warp interact with each other, we could have different configurations. It's essentially like being a tailor, essentially, and how you sort of create different fabrics. I'll explain what I mean by that. So, depending on the configuration of weft and warp, you could have different setups. The one is plane weave. The plane weave is a kind of configuration that the mechanical properties are identical in weft and warp direction. So if you look at here, plane weave example. So that was weft, right? So weft goes above one, under another one, above, under, above, under, above, under, as you can see. They call it plane weave. Because of this setup, the modulus of elasticity you get in that direction is called direction 2. That's direction 2, that direction 1. Oh, did it work? So, direction 2, direction 1. So, modulus of elasticity into E2, essentially E2, is the same as E1. Okay? There is also a possibility for another configuration. We call it twill weave. We use it quite a lot, actually. So twill weave and satin weave, we use that for wing construction. Twill weave is that its drapeability is good. Drapeability means, as I said, if you've got double curvature, you can form it a lot better. You can drape it, as they call it in technical terms. So then it's got 2x1 and 2x2 configuration. So these are things that you need to, if you go and work for a company and you want to order the material, you need to know exactly what these are. So in 2x2 twill, if you, what do you think is happening in 2x2? What should I explain it? You guys go ahead.
2 over, 2 under.
Exactly. So the weft goes over 2 of the warp and under 2, over 2, under 2, over 2, under 2, okay? Whereas in 2x1, I haven't shown this here, we would have 2 over, 1 under, 2 over, 1 under. Why do you think, what's the difference? What difference does that make really if you do that?
Properties in directions 1 and 2.
We'll change it slightly, but why would you go 2x2, 1? What was the reason really trying to migrate from that plane? What was wrong with that? And then we decided to go with that. Why would you do that?
Change the drapeability.
Exactly. So they first created that, implemented it, and said, oh, do you know what, it's not good enough. I can't drape it. What do we do? Let's change the weave. Okay? And they've come up with all different, and if you look at the research, I mean, thousands of research on that one and that one, I mean, it just doesn't stop. Another one is satin. What's happening here?
3. 3 over 3. Oh, wait, no.
Over 8 under 1.
Yeah, so the satin again, very strong, very drapeable. If you look at the wing of an aircraft, it's got a curvature. The wing is not flat. So they need something to go on top of it, and we use 5 harness satin, not 8 harness satin. So because the curvature is not too much, I don't have a too curved structure. So we use 5HS, they call it. 5. This is called 8HS, 8 harness satin. The one we use is 5 harness satin. It's a good example if you 1, 2, 3, 4, 5, 6, 7, 8. So it's going over 8 and under 1. Okay? If you look at the cross-sectional view. And I've put some explanation here for you. I'm just trying to improvise, not reading from the text here, just to make sure we are all going with it. So we've got another one, cross-plying week. What's happening here? Exactly. Very strong, and they've got some threads trying to, or if you look at it, it's a mesh, essentially a mesh of a thread or whatever you want to call it, putting everything together until it goes into the autoclave and it's cured and everything sticks together. Essentially, these are there for you just to keep things together, hold things together. And the king of all is unidirectional weave. That's the king that we use for high performance structure. Essentially, you've got fibers running along one direction. And because you've got fibers in one direction, the modulus of elasticity, if you get on these ones around 70 gigapascal, on these ones you get something between 120 to 180 gigapascal, depending on what kind of. So the strength is quite, the stiffness, not strength. Stiffness is quite a lot because all your load-bearing components are running. Yeah, go ahead.
So when you get to a unidirectional weave, does that only work in a sort of single plane of curvature?
I'm not with you. Can you elaborate on that?
Would you be able to drape it over a compound curve, or would it all start?
Yeah, these the unidirectional. Yeah. I mean, you've got fibers just running along a particular direction. Yeah, that's absolutely fine. Bear in mind, when it comes to composites, the problem mostly lies where you've got double curvature. If you've got single curvature, you're fine. If your single curvature is not too curved, you're fine. In the case of an aircraft, because of the aerodynamic requirements, it's not too curved. I mean, it's slightly, probably less than that. But when you're talking about the nose cone of an aircraft, the nose of it is severely curved, and generally they don't use carbon fiber; they use glass fiber because it should be the radar waves should be able to penetrate through it because you've got the radar at the nose of the aircraft.
Yeah.
If you use carbon fiber, it can't go through it. The radar waves can't go through it. So you need glass fiber. If you look at all the radar stations, all defense radar stations, you see those spherical buildings. They're all made of glass fiber, not carbon fiber. Because carbon fiber essentially will create a Faraday cage effect. It's very conductive. Carbon fibers are very conductive. In electric conductivity is high. So even you could use it as a battery. So we've got some research that use carbon fibers as a battery. So your structure would act as a combined battery and load-bearing structure. So that's how good they are. So if you create that, you're creating a Faraday cage. So the radar can't detect anything. Okay.
So is the main point for weave purely drapability, or is it also mechanical properties?
Mechanical properties. That's the main thing. Drapability is secondary. It's important, but the main thing of composite is specific strength. That's the key. That's why we use it. And then it's got enhanced fatigue, corrosion resistance, you name it. Fatigue, yeah. There's a lot to talk about. Now the fun starts. So far it's been just tagging along, being easy. Let's see what time it is, because I need your full attention here. We've been talking for 46 minutes. Okay. Let's have a break for 5-10 minutes. Okay, freshen up, get a coffee, tea, whatever you want, go to the toilet, and then I want you to come back, freshened up, because there's a lot of maths to go through, okay?
That's what I do.
Let's begin or resume. So this is the check-in code for those who were not present or outside. So OWTTAP. If you want to use it, please do so. So this section aims to address mechanical analysis of continuous fibers. By far, this is the most difficult part of composites. So if you master this, then you shouldn't have any problem with discontinuous fibers, because they are fairly a lot simpler than these kind of things. But let's see. I did upload basics of elasticity for you guys from a module aerostructures I used to teach. I hope you've gone through it just to become familiar with the concept. And for the sake of this module, I do encourage every one of you to freshen up your memory with respect to differential equations. Okay, so probably not so much for this mechanical behavior, but definitely so for buckling behavior of composites. You definitely need it. Partial differential equations, I know you hate it, but you need to know it so that we can address the challenges with composites. There is an assumption for composites which is worthy of mentioning, is that we assume the laminate is to be thin, and by laminate we mean a lot of plies stacked up together, cured. We call it laminates. So you've got composite plies, so the fibers impregnated with resin, and then you stack them up at different orientation, different angles, and becomes laminate. We'll see it. And so we're assuming that entire laminate compared to other dimensions. I mean, you've got width, you've got length of the laminate, but the height or the thickness of the laminate, we are assuming it's going to be thin. The reason for that, if we assume it to be thick, there are some other parameters that will kick in that make the formulation a bit more difficult. But it is still possible using finite element analysis methodology. And we also assume that the behavior is two-dimensional and elastic. So composites rarely experience inelasticity. It becomes so essentially like a spring. You pull it, it goes back linearly. So as a reminder for elastic theory, if you look at an isolated cube of material, we call it small, tiny epsilon dimensions, and by epsilon we mean infinitesimal dimensions, x, y, and z. If we isolate that material, which could be anyway, it could be on a structural load-bearing side of a vehicle, it could be a wing, it could be anything. Just as a reminder, that tiny component of material experiences a very general stress in three-dimensional space. So if we call this x1 axis, or you could call it x, x2, or you could call it y, it's up to you, x3, or you could call it z. That cube of material will experience some stresses. It is quite critical to understand what we mean by stresses, their signs, and their direction. But stress is essentially a tensor, not a vector, but we'll get to that. We've got two types of stresses: normal or direct stresses, as we call it, which is sigma 2,2, sigma 3,3, sigma 1,1. These stresses acting perpendicular to the plane of that cube of material. It is positive if its direction is to the direction of the normal of that plane. So that plane, the yellow plane, the normal of that plane is E2, acting to the positive direction of X2. Okay, so sigma 2,2 is regarded as a positive stress, positive direct or normal stress, because it's acting to the normal direction of the plane. The same could be said of sigma 1,1, because it's acting to the normal direction of that plane, this plane. The same for sigma. So everything you see here is shown for positive values or positive directions. On the other hand, you've got other stresses which are tangential to the surface or tangential to the plane. We call them shear stresses. Yet again, these stresses are regarded as positive if, one, they are acting on a positive plane, which is the case in this case, sigma 2,3, and positive plane means it's normal, is to the direction of the axis, and is pointing to the positive direction of x1, x3. The same could be said of sigma 2,1, sigma 1,2. So these are all positive. So we're defining normal stresses and shear stresses and their positive direction. Let me just get rid of these annotations so that you can see what's going on better. Is that clear so far? Any ambiguity before we proceed?
What's T?
T is the tensor. So the resultant of this and this and this would be a vector. And then it's just showing, but essentially these sigma ones are components of that T in different planes. Okay. You do recall from Hooke's law that suggests that if you've got a linear spring and you pull it down by a weight or a force, in this case a force, then that spring extends to 2x. If you extend it, if you use F, it extends by x. If you apply a twice as much force, then you will have twice as much displacement. And you would have x, F, and then that will be a linear relationship. And when we say a linear problem or a linear analysis, means that the relationship between the force and displacement is linear. There are some cases, particularly in the case of just a minute, in the case of metallics, that we will have this kind of relationship, which is not linear. But for composites, mostly you're dealing with a linear problem. And essentially, what Hooke suggests is that because it's linear, force is essentially equal to deflection times the slope of that graph. That K is the slope of the graph. So what do we call K? Stiffness. Okay. So that's Hooke's law in a nutshell. Yes. You have a question, right?
Your PowerPoint is slightly different to the one we've got. There's a couple of slides that you showed.
Yeah, I'll upload this. Don't worry.
So
Yeah, I'll upload it. Don't worry.
just for more complicated stuff in the future, it would be good to have the.
Yeah, you will have that. Don't worry. You'll have that. So this is the kind of Hooke's law as we suggest. Stiffness with deflection and forces. So if you use, essentially, if you divide forget about that. Don't want to make it complicated. And this is essentially stress equals to modulus of elasticity times strain. You all know it for a linear one-dimensional problem. Is essentially extension of the Hooke's law. Stresses are equal, so E modulus of elasticity is essentially stiffness. Okay, it's analogous to, So that E is analogous to K. Epsilon or strains analogous to displacements. Stress correlated to force. That's essentially what you get. And that's what you've been told. But what you haven't been told in your degree, and now you're becoming masters, is that material in general behaves like this, as you see on the screen. You're not, in practice, in real life, you're not dealing with just one stress. You're dealing with 6 components of stress in a 3-dimensional space. Stresses in 1, positive ones, 2, 3. Shear stresses, shear stress, shear stress. So normal, shear. Okay? And then stresses are correlated to strains associated with the strain, normal strain in 2 directions, normal strain in 3 directions, shear strains. So stress is correlated to strain using a matrix, often denoted in the textbooks as C matrix. We call it stiffness matrix. Okay? So now you're not dealing with just a modulus of elasticity, a very simplistic way of looking at the material. You're dealing with a stiffness matrix. So the E that you saw in the previous slide is a very, very simplified version of the very general behavior of material. Okay? What is interesting about the C matrix is that this matrix is symmetric. So as long as you know whatever is happening above the diagonal of this matrix, then you don't have to worry about the components here, because essentially you know that already. It's a sort of symmetric matrix. So essentially, what you need to deal with for a material, for any material, that you've got aluminium, you've got steel, you've got titanium, CFRP, GFR, you name it. Any material in this universe will be characterized in this form. Okay? So these are mechanical properties. They are properties of material. These are not something you calculate. Like modulus of elasticity, it's the mechanical property of material. So if you look at this for a very general method, which is not isotropic, it's fully anisotropic material, which has got behaviors in different, so it behaves differently in one direction than the 2 and the 3, totally uncoupled. It just behaves differently. Can you tell me how many of these, let's call it modulus of elasticity, you would require to characterize this material?
21.
How much? How many?
21.
21. So you need 21 parameters for the material. So if I told you steel, well, steel is isotropic, so it becomes fully narrowed down to just one modulus of elasticity. If it was something else, and we will see for composites how this develops or evolves, I need 21 parameters to be able to see how this material behaves under different loading. In the case of composites, there's a group of material, we call them orthotropic material. What is orthotropic material? Maybe you? Yeah.
What the word orthotropic means. What the word orthotropic means.
Yeah, what is meant by orthotropic material? Sorry, if I'm asking a question from someone, I'm not trying to single out someone or embarrass someone. It's just trying to instigate some sort of thought. I don't want to be talking all the time. If you don't know, that's fine. Perfect. No, that's fine. Anyone, somebody could go ahead. Either of you, that doesn't matter.
You got 3 properties that change depending on the 3 axes.
Give or take.
It's a material where they have different mechanical and thermal properties in 3 orthogonal directions.
Exactly, that's what it is. And that's applicable to composites. That's what happens. So essentially, what we will end up having, that this matrix for an orthotropic material will reduce to, so these components become 0. So instead of having 21 material constants that you need to know, how many do you need to know? 9. Significantly simplified. When you've got, so if you look at this plane, essentially for orthotropic material, it behaves in the yellow plane, it behaves a certain way. In the green plane, it behaves a certain way. And in the blue plane, it behaves in a certain way. So, and these are uncoupled. So what is independent, its behavior here is independent of its behavior here, and independent of its behavior there. So as you've got 3 perpendicular or orthogonal planes, it's called orthotropic material.
Why can we assume there's 0?
It becomes 0. We're not assuming it. So because what tends to happen for orthotropic material is these components means that if you say sigma 11 should be equal to C11 times epsilon 11, okay, at C22 epsilon 22, okay? So essentially this times that, this times that, this times that, okay? But what's going to happen for orthotropic material is that strain in that direction multiplied by that will contribute to the stress. Strain in the orthogonal 2 times that will contribute to stress in that direction. And the same for the epsilon 3, but shear components do not have any contribution. So 0 times that becomes 0, 0 times that becomes 0, 0 times that becomes 0. So the shear behavior does not contribute any to stress in one direction. Okay, that's what it's meant. That's why it becomes 0, because it doesn't contribute. It doesn't do. But if it was anisotropic, unlike orthotropic material, then those won't be 0. There's another way. So let's call this a generalized Hooke's law, as we saw in the previous slide. So if you want to find epsilons or strains, essentially you multiply, what do? Let's say you multiply both sides of the equation by inverse of C, that's your sigmaized, then you have epsilons, okay? So that's become 1. And eventually you find this. So epsilon is a strain essentially, which let's call it S matrix, or they call it compliance matrix. It's essentially the inverse of your K matrix. Okay? The inverse of your stiffness matrix is your S matrix. It's just a matrix operation. You can show it in this way, so that if you want to find the strains, you've got S times stresses. What is interesting about composites is that it's this matrix. And we will see. But essentially S11, S22, and S33 represent the extensional behavior of the composite. These ones represent the shear behavior of the composite, laminate. These 3 terms represent the shear coupling, or shear coupling. So when you shear, we don't have a paper, so when you shear it out, it shears the other way as well. So there's a coupling between shears in different planes. And this one, shear extension. If you've got a simple aluminium, this is aluminium, you extend it or you compress it, it shrinks or elongates. For the composites, it's a different story. Depending on the stacking sequence and all of that, if you extend it, it not only elongates but also twists. So you can make use of that action to benefit from it in the structural behavior. For instance, one of the things that they do for aeroplane to reduce or alleviate aerodynamic loading, it might sound quite primitive. So imagine my hands are the wing of an aircraft. If it was aluminium, it just goes up bending, down bending. For composite, it is possible to reduce the aerodynamic load. When it goes up, it also does that, twists, to reach or twist that way. Well, it increases the lift, but probably twists this way to reduce the aerodynamic. So if you use composites, you can't achieve this by metallics, but with composites, it not only goes up, twists as well. Just because of bending. So you've got bend. The loading is not changing, but the behavior becomes up, down. We're not using this for any aircraft at the moment, but there's a lot of research going on. They call it aerodynamic load alleviation. But this is one of the so by the use of composite, there is one of the possibilities that you can do. Or you can apply a temperature to the composite, make use of this coupling, and then when it heats up, it bends and twists so that the electrical conductivity disconnects. And then you cool it down, it goes back. The electric, like a switch, basically. There's a lot they can do. So the compliance matrix, instead of showing it in terms of S11 and S22s and all of that, you can see how it's correlated. Essentially, I'm having difficulty with this one. So the inverse of modulus of elasticity in 1, the inverse of modulus of elasticity in 2, in 3, shear modulus in 4, 5, 6, and all of that. You can see. Positive ratio. Eta is, they call it Lechnitzky buckling effect. They find it analytically. So essentially what they do is they test the material and analytically to try to find these eta and mu values. It's all analytical. But in our case, in the case of composites, it goes into the realm of material science, but in our composite it becomes further simplified. So we've seen what happens in general, okay, for general material, but how do we exploit that for composites? For composites, we assume it's thin and a 2D plane behavior, which suggests that stresses in the 3 direction, normal stresses, so that's 3 direction, through the thickness is 0. As a result, shear stress in 2-3 plane and 3-1 plane is also 0. This leads to the fact that therefore strains in 3, or how much it shrinks through the thickness or elongates through the thickness, is only dependent on stresses in 1 and 2 direction, and these strains also would become 0 as a result of shear strains being 0. So that long and complicated matrix really boils down to a simple one. Instead of having a 6 by 6 matrix, we would essentially have epsilon 1, epsilon 2, and bear in mind, the one direction we call it material direction, in the direction of the fiber, always for composites. 2 is perpendicular to the material direction, and 3 always through the thickness. That's the common convention we use day in, day out, and in any textbooks. So when we say strains in the fiber direction are essentially correlated using modulus of elasticity in 1, modulus of elasticity in 2, and shear modulus in times these stresses. So if I go back again, maybe you can see this long matrix is a 6 by 6 matrix. Now it is boiled down to a 3 by 3 matrix. A lot simpler. So that's what we deal with. And that was a consequential effect of assuming thin laminates and 2D plane behavior. Also, so that was the previous slide. Because the composite lamina, so we're talking, remember, we're talking about one sheet, one ply. You're not talking about laminates. So one ply or a lamina, and then if you've got lots of laminates, it becomes a laminate. We're not going there yet. We're talking about one ply in isolation for now. So because the shear behavior also is negligible, these components become 0, and as you can see, S1 is also given, S2 is given. I never remember these. I just, whenever I want to solve something, I just put it in front of me, and you don't have to memorize anything, just you've got it there. So your matrix is not only 3 by 3, now you've got 0 components. A lot simpler to deal with. But what it is common practice, instead of using S, just get rid of annotations, to show stresses in 1, normal stress in 2, so that's 1, that's 2. Shear stress 1, 2 in the plane. So you've got shear stress in that plane. Essentially, that's the shear behavior. We could call it sigma 1, 2. So that's sigma 1, that's sigma 2. So sigma 1 is direct stress in the fiber direction or loading direction. Sigma 2 is perpendicular stress here. Sigma 1, 2 is the shear stress in the plane 1, 2. Okay, I hope that makes sense. So that's 1, 2 in the plane. Then it's correlated to strains with respect to Q11, Q12, and the values of Q's are here. So basically, long story short, sigma is equal to E epsilon. Okay, for composites is this. It's not sigma equal to E epsilon. That's long story short. For a lamina, for a ply. Or you know it, you're not going to forget E epsilon, you know it from level 1 or level 0 really. E epsilon for composites is not E epsilon, it's this, it's a matrix. Okay? Sigma 1, 2, 1, 2, 0, 0, 0, 0, Q. And the Q's, we call them reduced stiffness of the lamina, and what they are is there. So essentially, if you look at Q11, it's modulus of elasticity in direction 1, positive ratio 1, 2, 2, 1. For Q12, Q21, so Q12, Q21 is symmetry. So if you've got that, that's the same. So Q12, if you look at it again, modulus of elasticity in direction 2, positive ratio and all of that. Q22 is here, is modulus of elasticity in direction 2, and all of that given. Q66 is essentially shear modulus. It's not difficult. I hope that made it. Just for one ply. Okay, one ply. We haven't gone to the laminate yet. Any questions so far? Yeah, your mind is. Yeah, I know. I know. I was expecting that, but wait until we get to the buckling side of things. It's going to get even more complicated. But yeah, the idea is that, let's go through it, and then probably I'll split this up into 2 sessions, because I want you to solve collaboratively a given problem, to consolidate whatever's been going on here. And I'm conscious of the time as well. How much time do we have? Yep. Okay. That's fine. Let's carry on. There is a lot more to come. Okay. That's fine. But that's not the whole story. We've been all talking about, again, we're talking about one lamina for now. So we characterize the behavior of the lamina or ply in 1-2 direction, which is this direction and this direction. 1 being along the length of the fiber, 2 being perpendicular to the fiber direction. And we said instead of dealing with sigma equals E epsilon, we dealt with stiffness matrix sigma, and then it was reduced stiffness matrix Q, and then we had epsilon. So far so good. And it's been associated to the stresses in 1 and 2. When it comes to composites, plies might have different orientation. It could be 0 degrees, 45, 15 degrees, 30, and by degrees being to the loading direction. For instance, X and Y here show the loading direction. Imagine you have a coupon on the tensile loading. Let's call it force here, force here. You could orient your plies depending on the design requirement. You can orient the plies in the loading direction. So we call it 1 and 2. We also have X and Y. Okay? So X being direction of the loading, Y is perpendicular to that. Or you could decide, depending on the stiffness that you require for your design, you can say, do you know what? I want to orient my plies this way. And this being 45 degrees. And your 1 and 2 directions are here. Or you might decide and say, instead of 40 degrees, I want it 15 degrees. It's well possible. It depends on what, 5 degrees, 20 degrees. Okay? But whatever I've been talking up until now, it's been in the 1 and 2 direction. Now we want to say, if we want to find stresses and strain in the X and Y direction, which is in the direction of the loading, what do we do? It's not rocket science here. It's a transformation matrix. So if I want to find stresses in X and Y loading direction, then that would correlate to stresses in the 1 and 2 direction with respect to this transformation matrix, depending on the orientation of the ply. As you can see, cos of theta to the power of 2 and all of that. You don't need to memorize it, it's there. Or you can, we do call that inverse of T. That's the name. So inverse of transformation. So the transformation matrix is essentially cos of theta to the power of 2, sin of theta to the power of 2 cos of theta, sin of theta to the power of 2, cos of theta to the power of 2, minus 2 cos, so on and so forth. The inverse of that is essentially that matrix. So if you pay attention to this one here, this one is essentially that one. Okay? So inverse of T. Therefore, it's written as, you see sigma x. That is here. That's the same. That goes here. And that goes here. The same could be said of strains. If you want to find strains in X, Y, and shear strain, you've got strain in the 1, 2 plane, and you use the transformation matrix. So let's go back again. I would be repeating this so many times you would be sick and tired of it, but there you go, we've got to do it. So Hooke's law, a simplified Hooke's law, was used to explain generalized Hooke's law for composites in the 1-2 direction, and 1 being material direction, 2 being perpendicular to that. Then we decided we might need, based on the design requirements, to orient the plies. So what happens in the stresses and the strains in the X and Y, which are the loading direction. So now this has changed into this. So stage 1, stage 2, stage 3. Clear? Any questions so far? Yeah, I know. I can see from your faces. Let's carry on. So, based on what I said, it's just plugging in some values So instead of having the epsilons, I'm just going to reduce the stiffness matrix, the strains, simplify the whole thing. Long story short, you don't need to worry about whatever I said previously. This is probably what you need to know. So we said sigma. So sigma 1, 2 was essentially Q matrix and then epsilon matrix. Now I want x and y's. We say sigma x and y is essentially, instead of Q, is transformed Q, or Q bar we call it. Okay? So all remember that. Q is a reduced stiffness matrix. Q bar is transformed stiffness matrix. As you can see, sigma 5, Q bar is matrix. Epsilon is epsilon y, gamma x y. And you will not, well, Q bar right here, depending on. And this is something you would be doing for your coursework, by the way. So I'm pretty certain by the end of this module you will master it. I'm pretty certain about that. And then if you want to do the same for a compliance matrix, it's all in there. Let's not go through it. It's the same concept. Instead of using for the stiffness matrix, we're using it for. So that's for the stiffness matrix. You can apply the same approach for S matrix, which, let's not go there for now. So we've dealt with the laminate, the ply. Can I borrow a paper from some? Maybe a pen. Can I borrow that pen as well, please? That's a very simplistic way of trying to explain. So that's one ply, right? One ply. That ply, let's say this particular ply, that's 0 degrees. So can you see the longitudinal fiber direction? Can you see that? Everybody can see that, okay? And this is the loading direction. So that ply is 0 degree. So that's 1, 2. One, 2. Can you see 1 and 2 or not? Okay. That's one ply. Then I decide because I want to be, so that's one ply impregnated. I'll put another ply on top of it. But this time, this ply is what? Why is it?
45 degrees.
What's that? 45 degrees, right? 45 degrees. One again. One is not changing. One is in the fiber direction. 2 is perpendicular to that. You might say, why do I need to do that? Is it not stronger like this? You might say that. But believe you me, if you don't have that, and you've got a lot, let's say bolts and fasteners, you will get high stress concentration and the whole thing breaks up. Having a strong material is good, but at the same time you have to compromise on stress concentrations and delamination. If you've got plies of the same orientation stacked up more than 3 times, your laminate delaminates basically, which is not good. So it's essential to have these 45. They're really good plies anyway. So you put that, you put another one on top. You've got another ply. Let's say this time, for some reasons, I decide to go 90. And you might say, why 90? Because I want to do it. So, yeah, 190. I put that 190 just in case. My load, although it's here, but what if something happens and I would have a load here? If I don't have any load-bearing fiber there, I'm screwed, basically. So I need to have that. And then let's say another 0 there. Another 0. So this is called a laminate. All different fibers. So far what I've been saying is about one of these in 1 and 2 direction and x and y direction. And the x being my applied load. Okay, my applied load. So I don't have to worry about that 0 degree because 1 and 2 is the same as x and y. There is no transformation. You can transform it, but you'll get the same stiffness matrix. That 90, I need to worry about it because the 1 and 2 directions are not the same as x and y. So I need to use that transformation matrix to convert everything into that x and y direction. That 45, yet again, I've got to worry about this because 45 is not, so 1 is that way, x is that way. So I'm dealing with each individual ply. But now I'm saying, okay, I know what happens with each of these plies, but how the whole thing comes together in the grand scheme of things as a laminate. How do they behave as a total, as a combined single structure, integrated structure? How does it work? And that's what we're trying to achieve. Okay. It is not easy to explain this kind of stuff as an instructor or lecturer. But we have to do it, don't we? So based on Kirchhoff hypothesis, we are assuming that when your laminates bend or goes through bending, these plates or the cross section of your structure is straight and stays straight after bending. Not necessarily correct, but it's a good assumption. As long as you assume there is no shear, it is possible. Well, most of the time, it's a good assumption, close enough to reality. But in reality, they call it zigzag theory. That plane, yeah. Not good, is it? That could be like this. That could do that. But, if you don't have shear, or the shear is insignificant compared to bending, you don't have to worry about it. Which is 90% of the time, that's true. Okay. So you have Z acting downward, Y, X. Displacement in the X, we call it U. Displacement in the Y, we call it V. Displacement in the Z, let's call it W. Look at AD. AD before deflection is here. B is a neutral axis area. C is an arbitrary point throughout this cross section. After bending, when it bends, A from there goes there. D from here goes here. B transforms into here, and C goes here. So your cross section experiences some displacements. Let's call it U0 in the X direction, and the 0 represents the mid-plane. So the mid-plane, which is B point, from here goes here. So you can see a U0 value being transformed. As you can see, the mid-plane goes there. So if I know where the mid-plane goes, that point Z essentially is U0, take away Z, or its location from the Z-axis, times beta, beta being the angle. Okay? So we always find the next location of the mid-plane, and then find the rest of the cross-section based on that. The beta is essentially the angle, or the rotation angle of the section. So if you use this into replace beta with its mathematical or differential equation. So beta rotation is essentially the slope. So the slope of deflection in this plane. So this is Z, this is X. Essentially you can see X and Y. So beta, you know it from mathematics, that is a derivative of deflection in Z with respect to X. The same could be said of here. And epsilon, mathematically, these are the things they haven't told you, very possibly, is that mathematically the way epsilon is explained or denoted is that differential of deflection with respect to the x-axis. That gives you epsilon x. So you just plug in all the values. So you've got the u is here. So if you put the u in here and differentiate that, essentially this is what you get. The same could be said of epsilon y and gamma xy, rewriting the whole thing into sort of into a matrix format. So essentially rearranging the entire three of these into a matrix format will give you epsilon x, epsilon y, gamma shear strength. These subscript zeros represents the midplane, which are strains. So the strain of the midplane in x, strain in midplane in y, shear strain of the midplane in x and y, plus z, curvature of the midplane. So essentially, if I want to find deflection of point C here after deformation, after loading, I'll end up knowing what the midplane is doing, plus z, or the location of that C with respect to the midplane. You'll see later on how the whole thing comes together. Okay, and then just for each ply you need to do that. So we also have the epsilons. We suggested that epsilon is q bars and then you have that one as well, comes there. Very complicated, but let's carry on.
Sorry. So is Z a constant?
Z, so this is my laminate, 3 plies laminate, right? That's the midpoint of through the thickness, which is the second laminate. So the Z is essentially, let's say this is the third laminate, the location of that with respect to the midplane. So if you look at the cross section, so let's say how many plies you have, 1, 2, 3, 4. That's the midplane, right? Then if you want to find stress here, that's the Z of that. If you want to find stress here through the thickness, that's the Z of that. So on and so forth. Okay? So it's really, again, we'll solve the problem. And I'm pretty certain you'll get the hang of it later, after some practice. So you'll get a summary of whatever I've been saying so far here. What tends to happen is this is showing a laminate with 1, 2, 3, 4. 1, 2, 3, 4 plies. Strain distribution through the thickness, this is the thickness of the laminate. Strain distribution is continuous, linear. There is no discontinuity. But the Q, reduces stiffness, is stepped. So you could have, for each ply, you will have different stiffness. Essentially that means for each ply, you've got different stiffness. For 0 degree, you've got 70 gigapascal. For 45 degree, you can have, 16 gigapascal. And then for 90, you will have 2 gigapascal. So you will have different stiffnesses stacked up together. That's essentially what it's saying. So stiffness of each ply is different. And therefore, if you want to remember sigma E epsilon, your epsilon is this, continuous, your E is stepped. Really, your stress is going to look like this. It's not continuous at all. So you get one stress for ply 4, and then it changes linearly, comes down, and then you go to ply 3. You've got different stress, different stress, different stress. Each ply has got different stress. So the key here, so that's why it becomes a bit complicated. Okay, it's not like metallics. So if it was aluminium, this is aluminium. You would have strain, and you would have stress, easy, nothing to worry about. And you remember from aluminium, how would you find stress? Do you remember that? Sigma is equal bending moment by second moment of area. You remember that? Simple, nothing to worry about. I mean, dead easy. But when it comes to composite, your M is the same. Your I and Y are not so easy anymore. It's not easy. That's why you get that complication. So for metallics, the stress is linearly distributed. For composites, it's not really. I mean, it's quite discontinuous. So it's a composite under a very general loading scenario. So you have forces in the x direction, and remember when we're dealing with composites, when we say forces, the forces are always expressed per unit width. So the unit is not Newton; it's Newton per millimeter or Newton per meter. Okay, so that's something you need to bear in mind. If the width is 200 millimeter, then you need to multiply that force by 200. Then you've got all the positive, torsion, bending moments, all is given here. So nx, ny, nxy, the forces in the x direction, force in the y direction per unit width, and the shear force nxy. Stresses in the x, y, and shear stress integrated over the thickness. So let's go back again, maybe that helps. So if I want to find, let's focus on ply 4. This is the stress distribution on ply 4. If I want to find, this is the stress, by the way. If I want to find how much force is in that ply, then how would I do it? How do I do if I want to find force? So essentially, force here in this ply, knowing the fact that the stress on top of that ply is sigma, at the bottom of that is that much. Okay, and that's essentially what's happening. We need to use integral. So integrate from half the thickness down half the thickness above, stress x. Okay, that will give you the force in that ply in the x direction. The same in the y direction, the same for the shear. And then because it's plies, it's not continuous, that integral sign changes into a summation format, and that will give you essentially, let me just zoom in a bit. So for each ply, that k superscript above k represents each ply. So you need to do that for every single ply. If you've got 100 plies, which is the case with the wing skin, for each ply, this holds true. For each ply, you need to find out the thickness of each ply, essentially times its stress will give you the force in that ply. Because later on we'll see when do we decide that the composite fails. We need these kind of stuff. Okay. I'm just putting these workings for your information to give you a brief idea, but you probably don't need all of this, and I will tell you exactly what you need the most, and that's it. As long as you know how these are derived, that's absolutely fine. The same could be said of bending moments. This time you've got the. Let me just go back again. Come back in. You've got the stresses. This time the same as force, but you've got a z attached to it. Let me go back again. What does it mean? Essentially, when you find the force here, and this is, let's say, the midplane. So the force here, or let's call it nx, times that distance is what? Is bending moments. So in essence, nx times z is m, bending moments. And what's happening here is exactly that. Essentially, these are the forces in each ply times their z, which will give you the bending moments in that ply. Put them all into one equation, into matrix format, and make use of all the relationship that we found. Eventually you come up with this kind of thing, and we can further simplify that as that, and that's the key here. So go through it in your convenience. I've uploaded 3-4 books. You can go through it in details if you're interested, which I highly doubt it, but you need to know this. That's the key for composites. So the forces and strains in composites are associated to each other. So nx, force per unit width in the x direction, force per unit width in the y direction, Remember, this is X, this is Y, and this is Z. And shear force in XY plane are associated to strains of the midplane and the curvature of the midplane. Okay? We call it a matrix. From now on, you need to know that as composite experts. A matrix, A11, A12, A16, and all of that, and the B matrix. Similarly, bending moments about X, about Y-axis, and torsion are associated to strains using a B matrix and a D matrix. In composite terminology, we use A matrix, we call it extensional, which purely deals with extension of the composite. Elongation, contraction. The B matrix, we call it the coupling matrix, which is to do when you extend something, it twists, which doesn't exist for metallics. So for metallics, really, that B matrix is 0. But you do have that A matrix. The D matrix is what? Is the bending matrix, as we call it, which does exist in both metallics and composites. But some of these components would be 0 for metallic material. So how do we obtain A and B and D? And that's what is required of you to do. Even for the coursework, you need to be able, as a composite expert, to be able to calculate A matrix by hand, B matrix by hand, D matrix by hand. You need to do that, at least for the sake of this module. But then when you go out in industry, there's software available that does it for you automatically. As long as you give it stacking sequence, it does it for you. So the A matrix, for each ply, basically, that's what's happening. For each ply, you will find the Q bar or inverse of the reduced stiffness matrix. You have all the formulation for each ply. So K represents the ply. For ply number 1, 2, N. It doesn't show it here. It's just not good, is it? So K is ply number. Imagine you've got N number of plies, ply number 1 to N. You do it for each ply. So Q bar of each ply multiplied by Z of the ply, the top and bottom of the ply, with respect to the middle plane. Z plane means the top of the above representation. Maybe shows it better. And we'll solve a problem today here, so don't worry, we'll get there. For the love of God, I don't know why this is doing to me. I can't do it, sorry guys. I'm trying to do it, but so look at ply K here. So ZK is the bottom of the ply. ZK minus 1 here is the top of the ply. So for each ply, essentially, ZK minus 1 is what? It's the thickness of the ply, essentially. So for each ply, you do that. If you want to find B matrix, pretty much the same as A matrix, but you use it square of Z. For D matrix, you use cube of Z. Simple as that. It's a lot simpler than it looks. We'll solve an example, don't worry about it. But here is the key. I think this is something to have at hand, if you like. It's a very good graphical illustration of what happens in composite. If you've got A11, A22, and A33, this is what we're talking about, the extension. For example, A11, you pull it apart, it extends. A22, you pull it apart, it shrinks on the other from in the perpendicular direction. A33 through the thickness. If you've got A13, so depending on the stacking sequence you have, you will have different. I'll take you through it. A13, you extend it, but you can see it is shearing out. Can you see above? So it's shearing. Also, if you've got this component populated in the stiffness matrix, when you extend the whole thing like this, you're trying to pull it apart, it also bends as well. If you have this component populated, is going to bend about the other axis here. So you can see it gets quite complicated. You don't have any of this with metallics. With metallics, all you have is this and this. Done, finished, dusted. With composites, you have all these complications. So as you can see, there's a lot of detail involved. Depending on what stacking sequence you use, it will provide or yield a different ABD matrix. We call it ABD matrix. It will give you a different ABD matrix. And it could be beneficial or it could be disadvantageous, okay? Beneficial in the way that you could make use of these coupling effects to reduce load, and if you don't do it properly, you might have secondary effects that will lead to the failure of the structure. So you've got to be careful. The stacking sequence has got its own rules and procedures. So above we just correlated forces with respect to the strains using ABD matrix. You could also say, you know what, I want to associate strains with forces, not stresses like above forces with strains. Essentially, taking the strain to one side and bring it, you inverse that ABD matrix will give you alpha, beta, and all of that basically. And if you want to know what alpha, beta, delta are, it's all given to you. You can use Excel to find, yeah.
So we don't do it in strain, we don't do it in stress, we do it in strain.
It's up to you, depending on the problem. If the forces are given, if the strains are given, you can find the forces using the above relationship, as long as you've got the ABD matrix. On the other hand, if the forces are given and you want to find the strains, which is mostly the case, normally you've got your structure, some loading is being applied to it, and you want to find the strains. This is what you use. Essentially, they're the same, interchangeable. I mean, you invert that ABD matrix, bring it to the other side, it becomes this. Depending on your problem and the knowns and unknowns in the problem. But this is mostly the case, because once you find the strains, and then you can decide, okay, each ply, you can find strains in each ply, and then decide when the entire laminate fails. We'll see later. Okay. So, there are some, as I explained, ABD matrices are purely dependent on the stacking sequence, how you stack up these plies, in what sequencing, how many of these plies you use. There are some common stacking sequences. One is called symmetric stacking sequence, and by that we mean, if you imagine the midplane, whatever you have on top of the midplane, you mirror image it at the bottom. So you've got your midplane, you've got 0, 90, just mirror image it, becomes 90, 0. That is called symmetric. And I've got it here actually, so I thought I didn't have it. So, and this is how we denote it. So I've got from the top 30 to 35, apply 35, which is orientation, that's theta. Then 20, then 40 degrees, and then in the bracket, S means symmetric. So essentially it's 35, 20, 40, then 40, 20, 35. Mirror image about the midplane. That's called symmetry. Well, the same as here, that looks like a 35, 20, 40, 40, 20, 35. That's how it looks. But for the simplicity, this is how we show it. Does that make sense or not? So this is called symmetric. So, and this is what we use for most. In industry, we always use symmetric, unfortunately, and that takes away the benefit of composites. And this is mostly driven by the fact that, one, we don't have confidence. The composites are relatively new. I mean, it's been around from 1980s, being used first in helicopters, but we're not really confident with it as of now. In the research community, they try to make use of these coupling effects and all of that, on symmetric laminate and all of that, but in real industrial applications, we don't do it. We don't feel confident, and our knowledge of composites and the way they feel is not really. It's very ad hoc. It's not really comprehensive enough. So, industry is lagging behind just because of that. So, the point I was trying to make is for a symmetric laminate, look at the ABD matrix over there. So the whole B matrix becomes 0. So there is no coupling. So it becomes essentially like aluminium and steel. What's the point of that? So the whole point was that I'm going to use composite, which is lighter, good. But I could make use of those B matrices to make it even better, but we're not using it. So as you can see, the full potential of composite is not being materialized yet. So in industry, we use all the symmetric ones. As a result, the B matrix becomes 0. So the symmetric laminate, all the information is here for you. There is, again, we use a balanced stacking sequence as well in industry. So balanced, symmetric, always remember it. You go to work in any company, balanced, symmetric is just given. That's it. So we also use a balanced stacking sequence. What does it mean? It means in your stacking sequence, for every theta ply that you have, you've got a minus theta. So if I've got 45 degree ply, I've got to have a minus 45 degree. I've got to have it. Because then the coupling comes in, and I will have some coupling impacts. So as a result of being a balanced one, those components, A16 and A26 become 0. And because it's symmetric, A16 and the other one becomes 0 as well. So most of the composites you deal with, unfortunately, in practice, is this. Come on. Pen. This is 0 as well. That's most of the composites you'll be dealing with in industry. And helicopter blades, and wind turbine blades, and wing skin, and fuselage, and all of that. That's given. Even for mechanical automotive applications. But you can see already we've just ignored a full potential of using composite with those coupling effects that is not being used. So balanced, symmetric. We've got cross plies, which means just 090, 090, 090, 090, 090. There is no 45s, there is no angle ply, there is no 15, 5, you name it. They're not good at all. I mean, we've just done the research for lugs, which is being published. You see the lug structures, right? Do you know what a lug is? Lug structure. So this is the a simple. You see it in landing gears. Yeah. So this is a lug, right? You use it in any engineering application. You've got straight-sided lug. You see these kind of structures in automotive industry, suspension systems, and landing gear, that kind of product. You've got a massive wallet. You've got a hole which is quite considerable. The size of that hole is considerable compared to the other dimensions. We've just shown different. We call it hard laminates, which is 0. As I said, it's a cross ply. 090, as you can see. 090, 090, 090, and then the mid-plane 090 and all of that. Okay, that's a cross ply. We've got a laminate called soft laminate, which is angle ply. Everything is 45, 45, plus minus 40, plus minus 40, and mid-plane 45. And we've got a quasi-isotropic laminate, which is balanced symmetry, which means we've got 45, 090, 45, 090, 45, 090. That's why, and we've shown that if you use the hard laminate, which everybody probably thinks this is quite strong because all the plies are in 0 direction, 090 direction. That's going to be strong, right? We've shown that this is the weakest kind of laminate we could use for a log structure on the tensile load. So if you've got a pin there, you just pull it apart. It's not good at all. Instead, that quasi-isotropic laminate, like this one, 45-0, is demonstrating a superior performance compared to the other sort of stacking sequences, even better than aluminium. For instance, so essentially it's a lug with a pin inside. We just pull the pin out to see which ones are stronger. So as you can see, just have a look. Let's have a look. These are the force displacements. So we've got the lug, we're just pulling it apart, measuring displacement and the amount of force. For the aluminium lug, You can see how it's behaving. Displacement, the force which goes to, let's say, 14 kilonewton. This is what industry is using. Landing gear is purely titanium, aluminium, and steel. None of that. If you look at a cross ply, as I said, the hard laminate, the cross ply, how much does it go up to?
9.5.
9.5. What's for the aluminium? 14. So if you use a soft laminate, which is all angled by 45 minus 45, how much is it? 10. Even 10. That's this is the stiffest one, stiff, but 10, 8. That one, which is not stiff as a stiff, is even better than the stiffest one. Okay. The coarse isotropic one, how much is it? 18 compared to 14. But you can see this is quite linear. Sorry, we're in position. So this is that's typical of carbon fibers. It's very linear behavior, linear elastic, as we said. If you look at the aluminium, up to a point is linear, and then it becomes non-linear and netting down, and the different failure mechanism. So it takes a lot of energy to make a break. But for the composites, it just goes to the max and then bang. You hear a bang noise. Okay. Just to show you how different stacking sequences impact the behavior of the composite.
Is there any uses for the hard or soft laminates then, or is it just that they're weaker?
Yeah, no, I think the outcome of this research is that if you want to make a log out of composites, use orthotropic. Hard laminate and soft laminate is just not good enough. It's not even comparable to aluminium, so there is no point in making use of it. So the next one, again, cross ply. I did mention that cross ply. The angle ply, which is the soft laminate, the angle ply. It just doesn't show anything here. Coarse isotropic, that's the one I talked about. Okay. So what I wanted to do, based on whatever I said, and that you didn't probably understand most of it because you need to solve things in groups. We are in groups. Tackle this example. Use Microsoft Excel and try to tackle this problem based on whatever you've seen today. Put one of the lecture notes next to you, maybe on the screen, and try to tackle it. Don't feel so let down if you can't solve it fully. That's absolutely fine. I understand that. I will also provide you with a tool, the way I've done it, and we'll provide you with a tool that we developed when I was in Atkins, and we use it for everything. And you can see how that's been organized to just give you some inspiration. Okay, so crack on with it. You've got until 12, is it? So the session is quite informal now. You can go out, come in. It's just the. Oh, sorry. I'm sorry. So sorry about that. So in fact, maybe I'll take you through it. Yeah, let's do this. Let's see.
Yeah, I'm just having a look there to see whether you've got the Spanish one.
We can suffer together. Alright, so this subject is definitely, we need to build
So this useful tool, let me just take you through it, and you could be inspired by that. I also have provided example 1 and example 2. Probably we'll be looking at example 2 next session, but example 1 is the one that you're dealing with right now. I've tried to solve it myself. Okay, no, I don't think I've made it available to you guys, so it will come up live.
Example 1 sample, example 2 is.
Example 2 is why? Maybe I hide it now.
Oh yeah, useful tourism there, for example.
Dang it.
Make it so useful tool is made available.
Access denied.
Can you refresh it? See if
Useful tools there.
okay. So that's something that you could be inspired by. Let me just take you through it. It's been a validated tool. I've tried it with many software, and it's good. The way this works is, let's make sure it comes up. The way this tool works is, if you go to the summary and define a material for your material, mechanical property. In this case, material ID 1, modulus of elasticity in 1, 2, shear modulus, Poisson's ratio, all of that is given. So you input all that data, and if you go further down, you create a stacking sequence. So for that, material ID, because it's composite, it is well possible to have one of the plies carbon fiber, the other ply glass fiber, the other ply Kevlar, which is the case for bulletproof vests. So you've got Kevlar and you've got glass fiber, okay, in different stacking sequences, or some of the UAVs, or even the wing of the aircraft has got CFRP, and the top, the outer mold surface and the inner mold surface is glass fiber to absorb the impact damage of debris and hailstone and all of that, really. So in this particular case, all the material in the stacking sequence is material 1. The thickness of each ply is given, the orientation of each ply given. If you want to make it symmetric, just press make it symmetric. It just creates mirror image on the bottom. So once this is created, if you go to classical laminate theory here, analysis, it will give you all the ABD matrices. So NX, as I said, forces per unit width, and strains, A matrix, B matrix, D matrix, and the coupling matrix. As you can see, in this particular case, it's almost 0. And if you want to have a look at, in terms of compliance matrix, the compliance is epsilon and the forces. So the compliance matrix is given. So whatever you do there, you can just double check it here as well, just to make sure you've done the right thing. And even for your coursework, you can use it as a validation tool. When you develop it, just check it with this one. Does it give you the right one? And that's a good approach.
But we can't use it before
No.
actual coursework.
No, I want to see it
So the coursework's you want to see the step by step.
like this one, like this tool. You can be inspired by that.
That's
So,
what I mean, sorry, this tool just shows you the.
For each one ply is connected.
no, it doesn't show you just the answer. It just shows you the working. So if you scroll down, you'll see how it's been worked out.
So you want us to do all the so you want to see that
Yeah.
calculation.
I want to see a file like this that you've developed yourselves. I've gone through the theory, and you've got a validation tool to make use of if you want it.
So for all of this, we're assuming properties of the matrix is negative, right? Because you don't actually put the matrix of the material.
No, when you give so this mechanical property, we'll see it in the next lecture probably, is given to you. This mechanical property is the combined mechanical property of the matrix and the fiber. So this is not, so the fiber itself, the modulus of elasticity is around 170, 80. When combined with the matrix, it will become 130 or 131. So this comes from the testing, tensile testing, the actual matrix, combined matrix and the fiber, not just the fiber. Okay. So it's different because I've got the information from different textbooks, right? But slightly different terminologies. EL means modulus of elasticity in the longitudinal, or 1. ET, modulus of elasticity in transverse, or E2. GLT is essentially G12. is interchangeable. Different textbooks, but these are the common ones. The new LT is Poisson's ratio in 1:2. So L is 1, T is 2. I would also make the solution that I've. Yeah. So can you double check if example 1 is also made available? Example 1 is it also made available or not? No. No, example 1 is the solution to this problem, and I can make it. So yeah, you should have it now, I guess. It should be available, example 1. So either start from scratch or be inspired by the files that I uploaded. It's up to you guys. Needs work in the group wise.